So the last session we learned how to find the complementary function for the given differential equation. So let I repeat a small part. We have a differential equations like a function of d. We have some function of d of y is equal to fx. So this is the general form of the differential equation. Okay, this is the general form of a differential equation. What is that phi of d? Phi of d is some function like this: d square plus 2d plus 1 of y is equal to x square. Okay, something like that. So this bracketed quantity is known as a function of d. This function of d of y is equal to x square. Again, in the last session we learned that we have some function known as CF, which satisfies the equation phi d of y is equal to 0. So I will write it by yc. Now what is yc? Yc is a CF complementary function. We denote it by yc. Yc is a notation. So what that yc is there, that complementary function is there. It is a function of that y is a function of x which satisfies this equation phi d of yc equal to 0 or phi d of y equal to 0. And that we already observed how to get that yc by just find out the roots of the equation phi d is equal to 0, that is auxiliary equation, and from the roots we get that function yc which satisfies this equation. Now suppose we take y as a new function. We are taking y as a function of yc plus some more function I am taking as a yp. Already we learned what is yc. Yc is a complementary function and yp is a particular integral or particular solution actually. So that is a thing that about a yp. Now how that yp is obtained, because yc is only the solution corresponding to this equation only. This yc is a solution for this equation, but we want a solution for phi d of y equal to fx also. So corresponding to non-zero RHS, there is some solution, and that solution can be obtained like this. Now let me replace this value of y as yc plus yp in this equation. If we replace that y by yc plus yp in that equation, we get phi d, value of y is yc plus yp is equal to fx. Now what happens if we take phi d inside, this operator inside, we get phi d of yc plus phi d of yp is equal to fx. But we know already this by equation 1 phi d of yc is a 0. This is a 0 because function of d, when we operate on yc, that always comes as a 0. So that is a complementary solution. This yc is a complementary solution for which phi d of yc is always 0. So we left with only this part. So this gives us a formula to find out yp. So the important thing, that formula is thus yp is equal to, now this phi d we take on RHS, it becomes 1 upon phi d of fx. And that's the formula. This is the formula to get a particular integral or particular solution of the differential equation. How to get a yp? By operating 1 upon phi d operator on the function of x. So throughout particular integral, all 5 to 7 methods, every time we use this formula only. Just a minute, I will skip to the internet. Okay, I hope I am audible. So here is that formula now. Yp is 1 upon phi d of fx. This is the formula we are going to use for getting yp only. So this derivation is not important. Whatever I shown you how the formula came for yp, so it's not important. Just I will sum up now. Sum up what we have to do it. What will happen? We will get a question like this: solve phi d of y phi d of y is equal to fx. This will be a question. This will be the example for us. Phi d of y equal to fx. Step one, we have to find out yc, complementary solution. And step two, we have to find out yp. And to get a yp, we use this formula, 1 upon phi d of fx. Yc we already learned. To get a yc, we find out the roots of auxiliary equation and find out yc. To get a yp, we use 1 upon phi d of fx. And last step, the complete solution. The complete solution of a differential equation is y is equal to yc plus yp, and that's a complete solution which contains a number of arbitrary constants are always involved only in yc. Yp is a free from arbitrary constant. There is no arbitrary constant there. And number of arbitrary constant involved in yc are equal to the order of differential equation. Okay, so that things we have to do it in every example now. We have to find out yc, we have to find out yp, and at the end we have to write down the complete solution as yc plus yp. And last important thing, which is a very, very important thing, you should know the meaning of the operator d. What is the operator d? Operator d denotes as a, yes, yes, anyone? Operator d, what it indicates? It's a d by dx. Very good. Okay, Rishang, yes, it's correct. Derivative operator, it's a differential operator. So what should be 1 by d operator? 1 by d operator, yes, anyone? 1 by d is a reciprocal of d there, so don't say dx by d there. Okay, so 1 by d is it's a inverse operator, and that is known as an integral operator. So it is integration dx. So these are the two important. This is one more important thing you should remember. Whenever you came across a d of some fx, you have to take derivative. And whenever we come across 1 upon d of fx, we take integration of fx. So 1 by d is an integration operator, while d is a derivative operator there. Okay. Any doubt? Is there any doubt? So if there is no doubt, let I move to the case number 1 for getting a particular integral. Is the case 1, exponential function. Remember, if you understand this only one slide, you can solve any example of exponential type there. So all possibilities are covered in the single slide here. So case 1 is our exponential function. Now how to get a yp, we already know. To get a yp is like this. Yp is equal to 1 upon phi d of fx, 1 upon phi d of fx. Now operating that phi d on fx, we can find out this actually, but instead of proving the result, so we are going to use the shortcut methods now. We are going to use the shortcut methods to get this particular integral. Now whenever we are going to operate this 1 upon phi d operator on exponential function, on exponential function, the method says just replace d by a. Replace d by a. So we are replacing d by a. We are replacing d by a there, so that we get a solution. So nothing we have to do it. Just replace d by a. So we get 1 upon phi of a into e raised to ax is a particular integral. That's our particular integral. But most important condition is there that when we replace d by a, that phi of a should not be 0. Phi of a is a not equal to 0, and that is known as the particular integral. I'm not going in the proof. If anyone is interested, I can show you a small quick proof for this, but better the proof is not required. Just we can use this formula, shortcut formula, to get a yp there. Anyone want the proof? Anyone want the proof? Yes? No? Okay, very good. Replace d by a and we get answer. So it is one of the simplest case to get a particular solution or particular integral. But this phi of a should not be 0. If phi of a is 0, remember this is not a case for this is not the possibility for case number 1 only. For first 3 cases, case 1, case 2 and case 3, whenever this phi of a is coming 0, the simple thing you have to remember, we have to multiply by x in the numerator, multiply x to the numerator, and differentiate denominator, so what is the case? Whenever denominator comes to 0, numerator you should multiply by x and differentiate denominator with respect to d only. So suppose d square is there, phi of d is a d square, so phi dash d will be 2d then. Okay, and then whatever that exponential function is there as it is, and after that you replace that d by a. So you'll get x upon phi dash a, x upon phi dash a into e raised to x. Remember this x, when you multiply, you are multiplying it outside the operator. Means this x will not be this side. X should be outside the operator. And that is the case. And you have to continue till that denominator becomes a non-zero. If suppose phi dash a is again 0, we have to do it like this way. X square upon phi double dash d into e raised to x, where this x square is coming outside the operator. Okay, so that will come to the examples, become more clear. So a simple case that we should remember, whenever exponential function is there, replace d by a. Whenever e raised to ax plus b is, replace d by a, we get a particular integral. Whenever a raised to x is there, now why we have to replace d by log a? Because a raised to x, this is again exponential function with the base a, but we can write it like e raised to log a raised to x, e raised to log a raised to x. So it can be written as e raised to x log a. Now this is just like e raised to kx, e raised to kx. What is k? K is a log a, and we already learnt when e raised to x is there, we replace d by a. When a raised to x is there, so we should replace that d by log a, because that we are replacing d by k. K is nothing but log a. So whenever a raised to x function is there, replace d by log a, replace d by log a. And lastly, when constant function is there, we replace d by 0. Why 0? Because we can write a constant as, suppose k is there, so we can write that constant as k into e raised to 0x. Okay, and we know constant can come outside the operator 1 upon phi d, but for yp of e raised to 0x, we replace d by 0, because 1 can be written as e raised to 0x there. Now come to the last part here, last part of the case 1. So here here the proof is shown. Here the proof is shown for a raised to x. The a raised to x is written as e raised to log of a raised to x, and that is kx, and we replace d by k, and where k is a log a. So indirectly we replace d by log a. So that is the case 2. And here is a constant. Whenever constant is there, constant into e raised to 0x can be written. Constant can be kept as it is, and we replace d by 0 there. So that is the case number 3. These are the 3 possibilities that we'll have in an exponential case. Any doubt in the shortcut method? Any doubt in shortcut method uh, to get a particular integral here? We'll see the example that gives you the more idea about how the examples are coming and how you should able to or how you should write there. No doubt. Let I move to the next slide then.
Sir, wait 1 minute, sir, please.
Yes, I will show you. No issue. You can write it. This part is not required. Remember, no need to write this part. This table is important. This is very important. You should just remember this part. Case 1, case 2, case 3. These are sub cases of exponential, because exponential can appear with the base e, base a, or constant. Constant also can be written in exponential form as e raised to 0x. Suppose 1 is there, 1 can be written as e raised to 0x there. Once you complete, tell me. Okay.
Completed, sir.
Okay, very good. We'll move here to the numerical. Now solve d square minus 5d plus 6 of y is equal to 3 times e raised to 5x. So this is an example. So this type of the questions are coming for 5 marks. This is a 5-mark question in the IMU paper. So in solution, now this question is divided in two parts. We have to find out yc and yp. So step 1, you should say yc. Now to get yc, consider auxiliary equation. Consider auxiliary equation. Yes, what is auxiliary equation here? D square minus 5d
D square minus 5 plus 6.
plus 6 equal to 0. Very good. So only function of d you have to equate to the 0 to get a yc. What are the factors?
D minus 6, D minus 1.
D minus 6, d, okay, d minus 6, d plus 1. That is d is equal to 6 and minus 1. Someone can write in reverse order also. That is also correct. Therefore, what is yc? Therefore, complementary solution we got. Yes. C1 e raised to 6x plus C2 e raised to minus x. Is that okay? Any doubt?
No, sir.
So that is the end of the step 1. You can highlight also because these two important steps are there that examiner are always looking for, getting yc and yp there. Now step 2, I'll write here step 2, yp. So to get a yp, we always use this formula 1 upon phi d of fx. Now let me replace phi d. What is the function of d here? That is d square minus pi d plus 6. And what is fx? Fx is a 3 times e raised to 5x.
So I think the factors are D minus 6 and D minus 1.
D minus 6. Yes, factors. Okay, just 1 minute. Minus 6d plus
Yes, sir,
next
minus
is
6. Sir, it can be 3 and 2.
Is that 6 and minus 1 correct, no?
Sir, if we factorize it minus 6D plus D, then minus 6D into D is coming minus 6D square, but A into C is 6D square plus 6D square.
Oh, just a minute here.
So minus 6 and 1, sir. Yes, sir.
Minus 6 and 1 are the roots. Is that?
Sir, what about 2 yes, sir.
Just a minute. This will come minus 6d. This is a plus d. Minus 5d you are getting, na? How you are saying? Okay, here is plus 6 is there. Okay. So that's the problem.
Yes, sir. Plus 6, sir.
To get a plus 6.
So d plus 6, it will become d plus 6.
D plus 6. Okay, just a minute.
No, sir, D minus 6 is correct. D minus 1 should be there.
Sir, it will be d minus 2,
but then
d
minus
minus
70
3.
will come. So all the factors are not correct then, I think.
Sir, it will be d minus 2. So it will be d minus 2, d minus 3.
Correct. Now
Yes, sir.
So here these
Yes, sir,
factors
yes.
are wrong. Very good. You should, if you written wrong factors, entire yc will be wrong there. Okay, good. So this is a minus 2, minus 3. Now it is okay. Minus 2, minus 3. So this is d is equal to 2 and 3. 2 and 3 are the correct factors. Is it okay now? C1 e raised to 2x plus C2 e raised to 3x. Now, okay, good. So you should write a correct factor. Okay. So 2, 3 are the correct factor. Good. Now come to the phi d. So this is the case. Now when we replace d by phi u, whether the denominator will become 0 or not, this you have to do the rough work, or you should know what are the roots. Actually, what are the roots of this phi d? They are 2 and 3. So when only you replace 2 and 3, when you replace 2 and 3, then only it becoming 0. But right now we have to replace d by phi u. So it should not be 0 then. So we get a direct answer then. So if you replace d by phi u, what will be the answer? 1 upon, replace d by phi u. It is a phi u square minus phi u into phi u plus 6 into 3 into e raised to 5x. You can give the reason here. We replace d by phi u. We replace d by phi u. This is the shortcut method gives, or this is the shortcut method says to get the yp there. And now this 25 and minus 25 gets cancelled. This is a 3 by 6. Okay, it's a 3 by 6 e raised to 5x, and that is again 1 by 2 e raised to 5x, and we got a yp. So this is the second important thing that we obtained. And don't forget to write lastly, thus y is equal to yc plus yp, and that's equal to, you should write all the terms here together, which is c1 e raised to 2x plus c2 e raised to 3x plus 1 by 2 e raised to 5x, and that is our complete solution for the given differential equation. Here is the end of the question, and this question will be, if it comes for 5 marks there. If anyone have a doubt, yes, you can ask. Step number 2, this one. Atharva, is this step you want or this one? No, this is just function of d is replaced, and fx, RHS fx is this one, that fx is taken here. Now whenever there is exponential function in the RHS, we just replace d by a. Now what is e raised to ax? Compare with e raised to ax plus b. If you compare with e raised to x plus b, the value of a is a 5. So replace d by 5 there. Replace d by 5 there. So whatever function of d is there, in that just replace d by 5 and you get yp. Now when you got yp, actually the yp we are obtained provided it is free from d. Now there is no d operator. See, function of d is there. So when we replace d by a, the operator d is removed there, and that becomes our function of x, and that function of x is yp there. This is a particular integral of the given differential equation. Is it clear? Okay, good. So tell me when you complete this.
No, so done.
Done. Okay. So second last question then. Question number 2. Yes, I want you should do it and tell me the answer. Given d square plus 4d plus 3 of y is equal to e raised to minus 3x. So that about in
Sir,
the
2 minutes, sir.
yes. This is in the required format only I am written. Yes, what about yc, anyone?
C1 e raised to minus 3x plus C2 e raised to minus x.
Okay, I will write it here first. Y equal to c1 e raised to
Minus 3x
Minus h.
plus C2 e raised to minus x.
okay, let me cross check here. So just
It's correct.
yes, it's correct.
It's correct, sir.
Okay,
That's correct, sir.
1 yc, yes, quickly I will write it. D square plus 4d plus 3 equal to 0. So it is obviously d plus 3, d plus 1. Okay, good. And d is equal to it is a minus 3 minus 1. Okay, good, correct. So that are the factors, and your yc is correct. Yes, nice. That is the end of the step 1. Just I will start step 2 and I will ask you only. Yp is equal to 1 upon 5d. In this case 1 upon 5d is a d square plus 4d plus 3, and e raised to minus 3x is there. What will happen when we replace d by minus 3?
Not satisfying the denominator, sir.
Yes, denominator, no, it will be 0, na? It will be 0.
Yes, sir, not satisfying.
Okay, okay. So we can say phi of a is a 0. Okay, so that the denominator is coming 0. When it comes 0, the simple thing that we have to do it, multiply by x. Okay, in outside the operator, don't take this side, don't write x that side, into 1 upon. Now can you tell me what is a phi dash d now? If this is a phi of d, what is a phi dash d here? Yes,
2d
anyone?
plus 4.
2D plus 4.
Yes, very good. 2d plus 4. So we are differentiated phi of d with respect to d. So derivative of d square is a 2d plus derivative of 4d is a plus 4, derivative of 3 is a 0, and e raised to minus 3x as it is. Now again we should check whether we can we replace d by minus 3, whether it will
Excuse
become
me, sir.
0 or not.
No, sir.
No, it is not. Okay, it is not coming 0, so we can replace them. So 1 upon 2 into minus 3 plus 4 e
Sir.
raised to minus 3x. So we can say uh, d by minus 3. We replace d by minus, and in this case you can say as phi of a is a 0, or instead of phi of a I will say as phi of minus 3 is a 0, because phi of minus 3, when we replace d by minus 3, that is becoming 0. So we multiplied by x, multiply by x outside the operator, and then write a 1 upon phi dash d that way, and now we have the
Sir,
answers.
why did we multiply by x
That
in
is
the
the method.
second?
We are not going the proof of the method. Already I told. So to get a particular solution, this is a way you should approach there. Okay.
सर अगर फर्स्ट डेरिवेटिव लेने के बाद भी सेटिस्फाई नहीं होगा तो फिर सेकंड डेरिवेटिव
Again,
लेंगे
you multiply by x and take second derivative.
तो वो
Okay.
x स्क्वायर हो
So
जाएगा ना सर
yes, outside will become x square and it become phi double dash d. Denominator will become phi double dash d there. So
Got
that
it,
way
sir.
you have to continue till the denominator should be non-zero. Right now it is coming 0. Minus 6 plus 4 is a minus 2. So minus x by 2 e raised to minus 3x. And that about y. And that about the end of the second part. Yp also we calculated. And lastly, thus y is equal to yc, that is c1 e raised to minus 3x plus c2 e raised to minus x minus x by 2 e raised to minus 3x. So this you should write that complete solution, because the complete solution is this one. Yes, 2d plus 4 because of the derivative. It is a phi dash d. See the method. The method say this
Yes, sir,
phi.
got it.
Okay, it is a derivative. X into 1 upon phi dash d. So if you complete it, tell me. We are going to the last numerical then for today. Okay, done. Very good. So the last question for today then. Question number 3, which is already I solved actually, you can see. So this is a solved question I completed already. So the question is here. Solve d minus 1 bracket cube of y is equal to e raised to x plus 2 raised to x minus 3 by 2. Remember, this question never asked in the exam. It is just created this question so that you should become familiar with all possibilities of exponential term. So one is in the form of e raised to x, another is form a raised to x, and third is a constant term. And whenever we have to calculate yp for these three terms, you can calculate yp of exponential separately, yp of 2 raised to x separately, and yp of constant separately, and you can add these three together. So that is only done. So case 1, step 1, to get a yc, we write an auxiliary equation. Auxiliary equation is a d minus 1 bracket cube is equal to 0. So 1 is a repeated factor 3 times. D is equal to 1, 1 and 1 again. So what will be yc? Yc will be c1 plus c2x plus c3x square into e raised to x. So I think there should not be a doubt in complementary solution. As it is repeated thrice, we get 3 constants c1, c2, c3 there in this fashion. Any doubt in yc?
No, sir.
No. Okay. Now step 2, yp. Yp is 1 upon pi d of fx. But instead of calculating that operating 1 upon pi d on entire 3 terms, we are applying this 1 upon pi d on first term separately, second term separately, and third term separately. So I'm saying yp1. So particular integral for first function. 1 upon phi d means d minus 1 bracket cube of e raised to x. So we are replacing d by 1 now. If we replace d by 1, what happens? The denominator is going to the 0. So multiplied by x here. What is the derivative of d minus 1 bracket cube? This is a 3 times
d minus 1
bracket square. Good. Okay, 3 into d minus 1 bracket square. But x is here. Why x? Because that denominator is 0 there. When we replace d by minus 1, d by 1 again it is coming 0. So again multiplied by x, so it is x square. It becoming x square, and now derivative of this part, d minus 1 bracket square. It is a 2 times d minus 1. So 2 into 3 becomes 6. Okay. But still it is repeating. If replace d by 1, still it is coming 0. So again multiplied by x, again multiplied x, and just differentiate denominator. Derivative of 1 upon d minus 1 is just 1 there. And we got the answer. So this is a particular integral for e raised to x. Okay. This is a term 1. Second term is a 2 raised to x. So it is 1 upon d minus 1 bracket cube of 2 raised to x. So the method says whenever a raised to x is there, replace d by log a. Replace d by log a for a raised to x there. So we just replace d by log 2. D by log 2 there. And we got yp. So it is very simple. It never becomes 0. Whenever we replace d by log of a, that pi of a is never 0 there. You get always answer quickly. Just you have to replace d by log a there. That about yp2. This is yp for 2 raised to x part. And now yp for minus 3 by 2 term. So it is a constant. So there is e raised to 0x is there unwritten, e raised to 0x. So we should replace d by 0 only. If we replace d by 0, we get minus 1 cube is again minus 1. So that becomes plus 3 by 2. So final answer will be yc plus yp1 plus yp2 plus yp3, and that is our entire solution, complete solution there. So this is an example in which each and everything is covered. Okay, like a raised to x case, constant term, exponential term, and how you deal with when the denominator is becoming 0. So all that things becomes clear like this. Okay, so that's a solved example. This way you should write in the exam also if you have to write. Any doubt?